Okay, everybody. Next up, we have Agustín Borgna. He's going to be talking about hybrid quantum classical circuit optimization with the ZX calculus.
Okay, thank you. So as Alex said, today I'll be presenting the work we did with Simon Perdrix and Benoît Valiron on optimizing hybrid or mixed quantum classical circuits. So let's get to it. So our setting is the usual one for mixed quantum circuits, where we have single qubit unitary gates, CNOTs, and control sets. We also have classically controlled operations, as control set and NOTs. We have measurement and qubit initialization from either a constant or from a bit line. And we have a reduced set of classical gates consisting of NOTs and XORs. Here we have a circuit representation of the superdense coding protocol. Our goal is to describe an algorithm that can rewrite this circuit back to the identity. The usual way of doing this is to find circuit patterns that we can rewrite into smaller patterns. The problem with that is that there is no complete set of rewrite rules. So we can always find bigger and bigger and bigger rules that we can rewrite. What we can do is sidestep this problem by using an alternate representation of quantum circuits using the ZX calculus. The ZX calculus is a it's a formal graphical language which can represent any pure quantum circuit. And it's represented by ZX diagrams. These diagrams are composed of two kinds of color nodes, the green nodes and red nodes we call Z spiders and X spiders. They also have a face. We have also a yellow constructor that represents the Hadamard operation. But here we will replace it by a special kind of edge we call Hadamard wire. Here, the degree 2 spiders I added are just identities. Well, the calculus comes with a series of rewrite rules. Between them is the spider fusion that lets us merge spiders of the same color. And also there's a color change rule that lets us change the color of a spider by adding some Hadamard wires. This may add to the complexity of the initial circuit, of the initial diagram, but it will be useful when optimizing because we can have diagrams with only a single type of node of spider. Another thing to note is that ZX diagrams only care about the topology. So you can move the nodes around without changing the interpretation of the graph. So using the ZX diagram, Simon Perdrix with Duncan, Kissinger, and Van de Wetering introduced a Clifford optimization procedure for pure quantum circuits. This is the same paper referenced by Sean in his talk about going there and back again. So there may be some intersecting definitions here. So the procedure starts by translating a pure quantum circuit into a ZX diagram in a special graph-like form, which then it optimizes with specially crafted rewrite rules. And finally, it extracts it into a smaller circuit. We will modify this operation, each of the steps, to be able to optimize mixed quantum circuits. For that, we have to, since the ZX calculus can only represent pure quantum circuits, we have to use an extension called ZX ground. This adds the ground operator, which is an information discarding generator. Since these grounds will commonly be connected to a single spider, we will call the whole constructor grounded spiders. The calculus comes with a couple of extra rules. Between them is the discarding rule that lets us delete any spider degree 2 spider connected to a ground. and also a connection rule that lets us connect and disconnect grounded spiders via Hadamard wires. So now, using the sex from calculus, we can define our translation from mixed circuits into diagrams, using a different approach than the one defined for the Clifford optimization. Here, we have to keep track of the labels of the inputs and outputs, because some of the inputs and outputs may be classical wires and some may be quantum wires. The diagrams we produce are in a special form we call weakly graph-like, where we have only internal Hadamard wires and green spiders. We also transform these weakly graph-like graphs into a strict version that doesn't let spiders be connected to more than one input, output, or ground. This will let us disconnect the grounded spiders from the edges and move them around the circuit. So now that we have a strictly graph-like diagram, we can talk about the underlying structure of the diagram in the form of an open graph. This is a simple graph with a defined set of inputs and output nodes. Here, in addition to the inputs and outputs of the diagram, we are marking the grounded spiders as outputs because they represent a discarding of information into the environment. When we translated the circuit into a diagram, we lost the idea of quantum and classical wires. Because now that we have a graph, we can move the nodes around, and it will be still the same graph. We can instead define a property on the underlying open graph called focus flow. This will give us a notion of order between the spiders that will be useful when extracting the diagram back into circuits. It's important that we preserve this G-flow property when optimizing. So we must restrict the rewriting rules we can use. So on the Clifford optimization by Duncan et al., they introduced two G-flow preserving rules to eliminate spiders with a phase multiple of pi/2. Those are the Clifford spiders. Here in these diagrams, I'm using dashed boxes to represent maybe multiple spiders connected. So in the Clifford optimization, they define an algorithm that applies these rules repeatedly, finding matches until it cannot match any of the rules and terminates. Since both of the rules delete at least one of the spiders, we know the algorithm terminates. We have adapted these two rules to the SEDEX ground. In addition, we also added a number of extra rules. The first rule, it's a discarding rule that lets us delete a spider connected to a degree 1 grounded spider. We also have the ground polypivot. It deletes poly spiders that are with phase multiple of pi connected to a ground spider. Having these two rules, we could use the same approach of just matching them against the graphs until we cannot anymore, and then stopping there. But we devised a way to find extra optimization opportunities by looking at the cut graph, the ground cut of the graph. So the ground cut is a partition of the graph between the grounded spiders and the non-grounded spiders. We then define the adjacency matrix of this ground cut as a binary matrix that encodes the connectivity between those two partitions. We also defined a new G-flow preserving rule that lets us apply row sum operation on that BHACC matrix by modifying the graph. Using this, we can run the Gauss elimination algorithm on the matrix. After running this algorithm, we end up with a matrix that may have some null rows at the bottom, which represent grounded spiders on the graph that are disconnected, and we can just remove them. There may also be rows which have only one non-zero element. And that means we have in the graph grounded spiders of degree 1. So we can use the discard optimization there. So after using Gauss elimination, we may find new matches to eliminate more spiders of the graph. So finally, we reach the algorithm where we first apply the original Clifford optimization to delete all the Clifford spiders we can. Then we run the Gauss elimination that will remove some Hadamard wires from the graph. Afterwards, if there are any disconnected grounded spiders, we can just remove them. And for the degree 1 grounded spiders, we just apply the discard rule. Finally, we can find matches for the polyground pivots and also apply that rule. Afterwards, we repeat this algorithm from the Gauss elimination until we cannot find any more matches. Since all the rules delete at least one spider, we know this terminates. So at the end of this algorithm, we obtain a smaller diagram which admits a G-flow, but we still have to extract this into a circuit. For that, we modify the extraction algorithm from the Clifford optimization, that is the same from Sean Stock, almost the same. Here, we use the same strategy where we start with a set of border spiders as from the output, and then sweep left, extracting spider by spider. Our contribution comes from two special cases that were not present in the pure reversible circuits. The first one is the fan-out case, where we have a single unextracted spider connected to multiple spiders on the border. There, we can just extract that as initializing a new line and applying some control sets. The second case is the fan-in, where we have multiple unextracted spiders connected to a single spider on the border. Since the diagram has a G-flow, we can prove that at least n-1 of those unextracted spiders are grounded spiders. So we can then just measure those lines, like measure a line and delete the result and discard the result and extract the fan-out case, the fan-in cases. So at the end, when we reach the inputs, we can look at the labels of the inputs or outputs we saved. And if there are any classical wires, we can just initialize a new qubit from them. And finally here, we can again apply the color changing rule to delete some extra Hadamard wires that were needed, some Hadamard gates. So at this point, we have reached a valid circuit, but you may note that all the internal operations are pure quantum. For example, here on the classical input, we are initializing a new qubit just to use it as a control for a CNOT and measuring it right after. We can instead find a way to classicalize the circuit. So we defined an algorithm for labeling the nodes in the diagrams to find parts of the circuits which can be realized classically. In this case, we can see that we detect that this can be done as a classically controlled X operation. So, and this, with this, we have reached the end of the optimization algorithm. So, in this talk, I described an optimization procedure for mixed quantum classical circuits using the formal ZX ground calculus. We introduced a number of G-flow preserving rules using the discarding operator and extended an extraction algorithm from these diagrams. This included a classicalization procedure to detect which parts can be done classically. We have implemented all this operation in the P6 Python library, and in the future we plan to benchmark its performance against real-world circuits with mixed quantum and classical logic. So that's all, and thank you very much.
Thanks, Agustín, for the very interesting talk. We have a couple of questions coming into the Slack channel. The first is from Eddie Shout. He asks, what are the row operations in the Gaussian elimination? i.e., how is the graph modified by them?
Okay, so the row operations we need, since this is a binary matrix, we only need row addition because the row addition in this case is applying an XOR over the connectivity. So we can, in this case, sum one of the rows to the first row and obtain another by complementing the connection. What we do is basically we choose, say the first row is say the first row is correspond to the grounded spider B, to the grounded spider B, and the second row correspond to the grounded spider U. What we do is apply this rewrite on the graph, and when we look at the matrix, it will change the connection. It will add the connection of the node B, of the node U, to the node B, so we can change that in the graph.
Okay. Miriam Backens asks, have you considered combining this with the work presented in There and Back Again, i.e.
Yes.
extending the extraction process to ZX ground diagrams when they have extended G-flow?
Yes, I looked into it and I found that most of the rules, like you restrict a lot the ground rules you apply when you have to look at the labels of the gadgets for the name. So you start saying, okay, we can only apply this when the spider is an XY and XZ. So I think it can be extended, but I don't know if it will improve much of the operations. This is something I would like to look more into.
Okay, so I think we have time for a couple more questions. So Alec Edgington asks, he says, I may have missed this, but does the representation cover all classical circuits? I think you mentioned XOR and NOT at the beginning.
Yes, this is a big caveat that we don't translate circuits having ANDs or ORs. That is not because we cannot represent them in ZX, but because the representation is too complex. So we can translate an AND as a TOEFL where we just discard a lot of outputs and things like that. And the thing is that, yeah, we can translate it as that and then apply all the optimization. But at the end, it's not simple to match where can we extract AND gates. Something that maybe using the ZH calculus we could do, because there the AND gates are more easily representable. But yeah, that changes a bit all the algorithms. So that's another step.
Okay, maybe as a final question, John van Vetering says really cool stuff. Is the procedure powerful enough to, for instance, fully reduce a quantum teleportation algorithm or dense coding, I guess, to the identity wire?
Yes, I think. So we changed. I haven't tested the final procedure on like real world circuits. We just did random generator, like generating a pure circuit and putting measurements in the middle and optimizing that and checking that we are optimizing what we should. So it works. But yeah, now I want to take a lot of like a set of benchmark circuits, of real world circuits, and try how it behaves there. It's something we have to do now.
Cool. Okay, maybe I'll ask a final one if the answer is relatively quick. So your representation doesn't. It seems to forget what is a quantum wire and what is a classical wire.
Yes.
Do you think that's a bug or a feature?
I think that's a feature because you may describe a quantum circuit that does, for example, you may start with this circuit here, that has some parts that, yeah, you could have done classically, but for some reason you generated that from somewhere and now you have only pure logic. I think it's nice to be able to extract more classical logic than there was originally. So